So my name is McKenzie Fontenot, for those of you who don't know me. Fortunately, I know most of the people in here. And today I'm going to be talking about Helm graphs and their zero forcing numbers and iteration indexes. But first things first, we do need kind of some background material definitions to get started. So that way we have kind of some intuition for what's going on. So the first definition we have is just kind of like a simplified definition of a graph. Most of these definitions and proofs are really simplified, kind of watered down versions of what's in the actual paper, just for simplicity's sake. But we have a graph G is a collection of pairs U and V such that U and V are in the vertex set of G, where V of G is just denotes the set of vertices on our graph. And then our next definition is the color change rule, which we're going to be using pretty heavily from now on. Sometimes we denote it CCR. And this is just when a blue vertex can force a white neighbor blue if and only if that white vertex is the only white neighbor of the blue vertex. And then our next definition is given a graph G and Z a subset of the vertex set of G, a set of blue vertices. We call Z a zero forcing set of G if and only if after a finite number of applications of our color change rule, all the vertices in G are forced blue. So there's no white vertices left. Just a few more definitions before we kind of get into the actual Helm stuff. We call the zero forcing number of G, Z of G, this is the forcing set with the minimal cardinality of all possible zero forcing sets of G. So like say for example, a forcing set that we could take could be just every single vertex in the graph. But obviously this isn't optimal, this isn't a minimal forcing set size, so we do have a minimal zero forcing set possible, and Z of G is just how we're going to denote that from now on. So our next definition is the iteration index of G, which is the minimum number of applications of the color change rule needed to force the entire graph G blue using this minimal zero forcing set. So like we could force one vertex at a time, for example, but if we can force more, we would want to do that so we have the minimum number of turns possible. And this is just kind of some notation here at the bottom. We have V, right arrow U, denotes a blue vertex V forcing a white vertex U blue. Our last definition for kind of like our precursor stuff is just for zero forcing change. This one's kind of a bit more technical than the other ones, but we just have a graph G and we let Z be a zero forcing set of G and S be a chronological list of forces of or on Z of G. And then if we have this set of vertices here is a subset of the vertex set of G, and for each I less than n-1, we have V sub J forces its neighboring vertex. Then we call this set a zero forcing chain under S on G. So just a little example here, just to kind of get some intuition going. We have two graphs here. They're the exact same graph. We just called a path on 5 vertices. If you look at this top example, we have 2 blue vertices in our forcing set on turn 1 or application 1 of the color change rule. Each of these vertices forces outwards because it's their only white neighbor. On application 2, we get this last vertex over here. So this set can force the entire graph, but it's not an optimal or minimal set. Because if you notice down here in the second graph, we can force the same exact graph, but using a smaller set. Because on turn 1, we just come to the right and we just keep going until we get the entire graph forced. So this would be our minimal forcing set. So next up we have the wheel graph, and we just need this definition because we use the definition of the wheel graph in our definition of the Helm graph, so we use this to kind of build up. So we just have that the wheel graph is just defined as this set of vertices here, and we define our edge relations such that 2 vertices are in the edge set of the wheel graph if and only if one of the following is true. This definition is kind of like hard to look at. I think, at least for me, it's not very intuitive if you just look at the definition, so pictures I like a lot more. So we just have a center vertex, which we're just going to call V naught or V sub 0, and then just a circle surrounding this center vertex where each vertex along the outer circle is connected to the center vertex or forms an edge with that center vertex. So next up, we have the actual definition of our Helm graph. Again, it's kind of hard to like look at. There's a lot of indexing going on. It's kind of hard to see, but if you look here, you'll notice that we do have the definition of the wheel graph in the definition of our Helm graph, which is why we kind of needed to throw that in there. And we just have the following edge relations defined. Again, kind of hard to see, so let's look at a picture. So if you look, you can very clearly see where the wheel graph is in the Helm graph. The only difference is that from each of these vertices right here along the outer circle, which I'm going to call spokes from now on, they each have a vertex coming out of them, which we're going to call pendants. So each spoke has a pendant vertice coming out of it, which is where we get the definition of the Helm from. So our first theorem that we have is that the zero forcing number of the Helm graph is n over 2 ceiling for n greater than or equal to 5. We're just kind of give a simplified version of our proof. So we have that n is the number of pendants on the Helm graph. So if we have like H8, that is the Helm graph with 8 pendant vertices around it. We know that each zero forcing chain for the Helm graph can have at most 2 pendant vertices. So we know that if the size of the graph is n, we can have at most n over 2 pendant vertices, or at most 2 pendant vertices in each forcing chain. So we get n over 2 ceiling as our lower bound, because if n is odd, then we're going to have one forcing chain that has 1 pendant vertice in it as opposed to having 2 in it. So the next thing we need to do is establish n over 2 ceiling as an upper bound. The first thing we need to notice is that if we want to show something as an upper bound for the zero forcing number, all we have to do is show that we can force the graph using a forcing set of that size. So we can kind of kill 2 birds with 1 stone here. We can show that we have n over 2 ceiling as an upper bound by forcing the Helm graphs using a vertex set of this size. So we're going to kind of combine this proof with the proof for our iteration indexes later on and just kind of get both of them in one turn. So for now, we're just going to kind of come back to that. So the next thing we have is the Helm iteration index. Due to the nature of the Helm graph, the iteration index is dependent upon the optimal zero forcing set given and on the congruency of n mod 4. So our next theorem is that the iteration index of the Helm graph is 6 if n mod 4 is congruent to 0, it's 4 if n mod 4 is congruent to 1, and 5 if n mod 4 is congruent to either 2 or 3. For time's sake, we're only going to focus on our proofs and outlining them for one of these congruency classes, but all the other proofs follow really similar constructions. So the congruency class we're going to focus on is n mod 4 congruent to 0, where the iteration index is 6. So here we have just a picture of the forcing set that we're picking. Notice n over 2 ceiling is just 4 here because we have H8, so we have 8 pendant vertices. These blue vertices are the vertices that we're taking to be in our forcing set. So we're taking 3 in a row, and then we're going to take 1 vertice over here. That's 1 away from our first one that we picked. So this complicated looking thing right here is just denoting the forcing set that we're picking. If you notice, we have pi from I ranges from 1 to 3. This is just the 3 pendant vertices that we picked over here. And then union, these sets of vertices right here. If n is large enough, then we're going to have to skip 2 vertices, take 2, skip 2, until we eventually get to this last vertex right here, which is just this lone vertex that we have by itself. So first thing to notice here is that the pendant vertices which we take in our zero forcing set can always force their corresponding spoke on turn 1 because it's their only white neighbor. So each of these vertexes that's blue can immediately force down on turn 1 because their only white neighbor is the corresponding spoke. Again, pictures I think are just a lot more intuitive to look at instead of complicated looking proofs. So we're just going to look at a picture for now. So on turn 1, each of our blue pendants can force down to their corresponding spoke. And if you notice, after turn 1, we have 3 vertices in a row right here. So this middle vertex can force down and force the center on turn 2 because it's its only white neighbor at that point. After that, we can get 2 more vertices. We get some rotary action going around the outside. We can force left this way and right this way to get both of these spokes. On turn 4, the center vertex is going to force out to this vertex right here, or I'm sorry, this vertex right here is going to force over. After that, on turn 5, the center vertex is going to force out to this spoke. So now we have all the spokes forced blue, so we can force out for the rest of our pendants and force the entire graph in 6 turns. And if you notice, each of the forcing chains that we look at has exactly 2 pendant vertices in it. For example, this vertex has this pendant vertice. It's going to force down, over, and back out. It can't go back down, so it has exactly 2 pendant vertices in it, as does each forcing chain because n is even, which is what we want. So the next definition that we have is the generalized Helm graph. Really similar to what we're calling the restricted Helm graph, or just the Helm graph with 1 pendant vertice corresponding to each spoke. The main difference here is if you look in the definition, we have our pendant vertices labeled here. We've just added another level of indexing. This is just going to correspond to the fact that each spoke can have multiple pendant vertices coming out of it, but each spoke has the same number of pendant vertices. So like this one can't have 2, well, this one has 7, just so they're all the same. But this is an example of a generalized Helm graph. So our first theorem with the generalized Helm graph is that the zero forcing number is m times n minus 1 plus 1. Again, we're just gonna kind of go through a simplified version of these proofs. But first things first is we need to show that the zero forcing number is less than or equal to n-1 times m plus 1, establishing an upper bound. Again, the easiest way to do this is just to take a zero forcing set of this size and show it can force the entire graph, which we're going to do later on when we do our iteration index. So we're just going to combine those again. But just to kind of get some intuition going before we keep moving on, this is a picture of our zero forcing set for the generalized Helm graph. So we take every single pendant on each spoke except for one, and then we take our center vertex. So the reason we need to do that, so first thing we suppose is that for each of these spokes, we need to take at least every single pendant vertex except one, which is just what this is saying here, this n-1. And we do that, we prove this by supposing that we could take less than this. So suppose that there were 2 white vertices on just one of these spokes, then we wouldn't be able to force the entire graph, because that would mean that this spoke right here, even if every other part of this graph was forced blue and there were just 2 white vertices here, we wouldn't be able to force the graph, because this spoke here would always have 2 white neighbors, and this is the only vertex that can force its pendants, so no forcing would be able to happen. So we have to have at least n-1 pendants on each of these spokes. So the next thing we need to do is show that we have to have this center vertex. So again, we suppose by way of contradiction that we can take just n times n-1, so take all of these pendant vertices that we have here, just minus the center vertex. So then on turn 1, these would all force their corresponding spokes, but then we run into the same problem. We're immediately stuck because each of these spokes would have 2 white neighbors at that point. They would have their leftover pendant vertex and the center vertex, so nothing would be able to force. So we have n times n-1 plus 1 as our lower bound and our upper bound, so we have equality. So our next theorem is that the iteration index of the generalized Helm graph is 2. This one's pretty intuitive if you just look at a picture. It's pretty quick. So on turn 1, one of these pendant vertices on each spoke is just going to force down, force the spoke. Since the center vertex is taken in our zero forcing set, we can force back out and get all the pendants on turn 2. And our proof is just done by way of contradiction. Suppose that we could force the graph in one turn using a forcing set of this size. Then on turn 1, we would get all of these spoke vertices, but then we would still have one pendant on each of these that we couldn't, or that haven't been forced. So we have to force it in 2 turns. This is all part of our larger project. Where we're ultimately hoping to get to is hub graphs. Hub graphs are just kind of like a combination of 3 different types of graphs, the Helm, the gear, and the target graph. If you look, it's kind of easy to see where the Helm graph is coming in. In this graph, we have all of our pendant vertices over here. So we're just kind of working our way up to the hub graph, and this is where we would ultimately like to end up with our research project. And these are just some other contributors on our project. A lot of these people are actually in this room now, so that's pretty convenient. But that's all I have for you guys.
Well, thank you, McKenzie. So we have an opportunity to ask questions of McKenzie. Yes, Isaac, we can all clap silently with the icons there.
Thanks, Isaac.
There we go. So any questions for McKenzie on her presentation? And I'll count. Oh, there we go, Isaac. Let's unmute Isaac. There we go.
Hello. Hi, McKenzie. Great job. So what it seemed like to me was that the definition of the zero forcing set for the restricted Helm graph was a lot harder to define than the generalized Helm graph. Would you say that, for example, the more vertices it takes and like the harder it is to actually make a zero forcing set, the easier it is to prove it and find it? Like if there's more restrictions on how many vertices you have to have in a zero forcing set, does that make it easier to actually find the proof?
I mean, I would say for sure it is, because I mean, when you look at the proof for the generalized Helm graph as opposed to the restricted Helm graph, I mean, it's one of them is like 2 lines and the other one is like 3 pages. Because the more vertices you have to take, kind of the less options you have and the less vertices you're going to have to force in the future. So I think it just kind of intuitively would make sense that the proof is going to be easier because you have less options as far as turns go and less options for your zero forcing number. Like, you know, you're kind of restricted. You have to take certain vertices in your set. So it does, I think, make things easier.
It's kind of like how we might have said that the worse your zero forcing set is, like the more vertices you have to spend on blue vertices, the worse your zero forcing set is, the easier it is to find the iteration indices. Because if you're filling like 90% of the graph with blue vertices, it doesn't take very long for all of it to become forced.
Yeah, exactly.
Cool. All right, that's all my questions. Thank you.
Thank you for the question, and thank you for addressing that, McKenzie.